To summarize the discussion that we had until now, there are essentially 3 steps in the computation of DWT. Although there are 3 steps, as far as the user is concerned, the user has to specify only the low pass filter, which is the first step, and the low pass filter is denoted by h of n as per our notation, and then one computes the high pass filter using equation 14, which is this g of n is minus 1 raised to 1 minus n h of n. In fact, I would ask you to do a simple exercise to show that if h is a low pass filter, indeed g is a high pass filter. How would you do that? Well, there are several ways of doing it, but one simple way perhaps is to consider these filters in the frequency domain, that is the frequency response functions of these low and high pass filters, and show that g of omega at omega equals 0 is 0, because that is one of the key requirements of a high pass filter. And in showing that, keep in mind that h of omega at omega equals 0 is not 0, because it is a low pass filter. In fact, h of omega at omega equals 0 as per our requirements on the h is root 2. So, if you recall, look at this equation 6, it clearly tells me that the frequency response function of the low pass filter at 0 frequency is root 2. Using that and this relation in 14, I would like you to show that g of omega at omega equals 0 is 0. So, it should be a fairly simple exercise. So, let us move on with the 3 steps for computing DWT. So, as a user I specify the low pass filter, compute the high pass filter, and in the second step I compute the scaling function and the wavelet function as well as their scaled versions using the scaling relations that we had seen earlier. So, specifically the scaling relations that we are referring to is 10, which tells me how to compute the wavelet given the scaling function, and the high pass filter, as well as equation 3, which tells me how to compute the scaling function given the low pass filter as well as the scaling function at a finer scale. So, we use this iteratively and we can compute the scaling function and wavelets at different scales, because I know h and g, and of course, I have to start off with the scaling function at some scale, but we will talk about that in the next lecture, where I will show you how to construct the scaling functions and wavelets given h and g. So, let us say you have done that. Going back to the 3 steps, so we have done step 2, starting from h and g, we learn how to compute this phi and c and the scaled versions. Then remains the third step, which is that of computing the projections and the coefficients, of course, on to the subspaces V m and W m. That is essentially we want to compute the approximations and details at a level m. M is generic, so we will compute approximation details at all levels, and in computing those approximations and details, we would invariably compute the coefficients denoted by the small a and small d at the respective scales. So, these are the essential 3 steps for computing the DWT. It is quite different from the way you compute CWT. Now, the main difficulty with these 3 steps is it is computationally quite demanding, and we should find means of computing this in an efficient manner, and fortunately for us there exists an efficient manner, as I had mentioned earlier, where you can bypass step 2, which is the computation of the scaling function and the wavelet function from the filters. Without actually computing the phi and psi, I can directly compute the projections, the essentially the approximations and details and the coefficients from the filters themselves, and that is the key, one of the key ideas in the fast algorithm. But a more important point is that we can do this in a recursive manner. What do we mean by recursive manner? So, given the scaling function coefficients or the scaling coefficients, that is what we call the small a m, and the detail coefficients or the wavelet coefficients, which again we denote by dm. Given these two at a level m, the scaling coefficients and the wavelet coefficients, I can compute the scaling functions and the detail coefficients at a coarser level, that is a m plus 1 d m plus 1. In fact, I do not even need dm, I just need am, as we will see shortly. Once I have a recursive relation like that, then all I need to do is compute the coefficients at one scale and then recursively compute the coefficients at all the subsequent coarser scales. Once I have the coefficients, obtaining the approximations and details, that is the big A and big D, involves simply reconstructions, and we will talk about that, and we will see that there exists a fast algorithm for doing that as well. Now, the question is, how is it possible to derive a recursive relation? What is that relation? Now, to compute this recursive relation, we use two sets of equations. The first set of equations are the expressions for the coefficients themselves, which are given in equation 16 and 17 here. We know already that the approximation coefficient is the inner product of x and the scaling function at that scale, right, and the inner product is given by this integral. Strictly speaking, in the integral I should have a phi star, but since most of the times in DWT we use real valued wavelets, I have dropped the star for you. So, it is integral x of t phi m subscript k of t dt. Now, k is the index that is that keeps track of the time point at the mth scale. Likewise, the detail coefficient dm of k is a inner product of x and the wavelet at that scale. Once again, I have the integral expression here. So, this is one set of equations, and the other set of equations now that I am going to use to derive a recursive relation are the scaling relations themselves. Remember, the scaling relations allow me to compute the basis functions for a coarser scale in terms of the scaling functions at a finer scale. So, as equation 18 and 19 show us, the phi at the scale m, in fact, it is not exactly phi at scale m, it is phi of 2 to the minus mt minus k. The phi at scale m would be what you have on the left hand side multiplied with 2 to the minus m by 2, right. So, let me just show that to you. So, phi m comma k is 2 to the minus m by 2 times phi at 2 to the minus mt minus k, and likewise the wavelet at scale m and at location k is 2 to the minus m by 2 psi 2 to the minus m t minus k. Once again, I should remind you that this k helps me keep track of the time index at the scale m. Remember, the indices, the translation indices change with scales because I am moving the windows proportional to the widths or the scales of the basis functions or the scaling and wavelet functions. So, what you have in equations 19 and 18 and 19 are relations for this, right, and the relations in 18 and 19 are nothing but generalization of the scaling relations that we have seen earlier. In fact, what we had seen earlier is that phi of t by 2 is root 2 sigma, what we had seen earlier is phi of t by 2 is root 2 sigma h n phi of t minus m. So, this is nothing but the special case of this where m is 1 and k is 0. So, as you can see here, I substitute in that equation 18 m equals 1 and k equals 0, I will get this relation, and likewise I had the scaling relation for the wavelet that we have seen earlier as well. This is once again a special case here. Of course, if I bring the root 2 here, then I have root 2 to the left here or to the left here, then I have psi m comma k. But as you can see, the relation that you have in 19 gives you this when you evaluate it at m equals 1 and k equals 0. All right. So, the set of equations that I have for the approximation coefficients and the detailed coefficients and the scaling relations put together will give me the recursive relation, right. That is how. So, what is the key idea? The key idea is I start with equation 16 because I want to compute a m, that is the approximation coefficients at level m given the approximation coefficients at level m minus 1. Remember, we know that V m and W m put together give me V m minus 1. In other words, V m is a subspace is a subspace of V m minus 1 and so is W m. Therefore, to compute A m and D m, I only need A m minus 1s which live in V m minus 1. So, I need a recursive relation for A m in terms of A m minus 1. What do? I begin with the expression that I have in 16, which is for the projection coefficient, and observe that this is x of t times phi m k of t dt. All right. And what do I do now? I expand phi of m comma k, which is 2 to the minus m by 2, I know this already here, phi of 2 to the minus m t minus k dt. And at this point I bring in equation 18, which tells me how this term is related to the basics functions for scale level m minus 1, right. So, using equation 18, I rewrite this integral as x of t times sigma h of n times root 2. So, now let us not okay. So, let us write sigma h n here root 2 and then I have 2 to the minus m by 2 already here times phi 2 to the minus m minus 1 times t minus what else do I have? I have a 2k and I have an n. So, let me minus 2k minus n dt. So, all I have done is I have substituted for phi using equation 18. Now, what we shall do is first interchange the order of summation and the integral, right. So, when I do that I get sigma h of what, and an additional step that we shall do is we shall call this 2k plus n as some L, so that I realize n is L minus 2k. So, instead of n here I write L minus 2k and then I have 2 to the minus m minus 1 by 2, where I have clubbed root 2 with the 2 to the minus m by 2, and then now I have phi 2 to the minus m minus 1 t minus L dt. Now, this is very nice. Of course, there is an integral here, I am sorry. So, integral of this times x of t dt. The reason for changing the order of the summation and integral is will now become obvious. I recognize this part here. What is this? This part here is nothing but a m minus 1, right. this is A m minus 1 at what time? At lag L or at the translation index L, because that is by definition. If you look at 16, that is exactly what we have, but we have it for m, right, we have it for m, but if I were to evaluate for m minus 1, now L is the translation index that will keep track of the time locations at scale m minus 1 or level m minus 1, that is it. So, I have now this familiar relation for A m k in terms of A m minus 1. So, if I were to write here the relation, the final relation that I have A m of k as sigma h L minus 2 k times A m minus 1 L. It is fairly obvious that this is a convolution expression, right, it is a discrete time convolution, and here L runs from minus infinity to infinity. But the only difference between the regular convolution and this one, if this was only a convolution, then I should have had only a k, then that makes it a perfect convolution, but I have a 2 k here, and therefore, this is convolution plus downsampling. So, think of this convolution being implemented in 2 steps, one a regular convolution. So, think of this as k prime and k prime is 2 k, right. So, in fact, you can say this, if this is k prime, this is k prime by 2, k is k prime by 2. So, either way you look at it anyway. So, we will now that you have understood hopefully that this is convolution followed by downsampling, I can write this as convolution of h with A m minus 1, but followed by downsampling. So, A m of k now is very easy to obtain. All I do is given A m minus 1, I convolve with h. That is a beauty. H does not change with scale at all. We have noticed that earlier. H remains the same as long as I am looking at 2 successive scales. So, I am looking at 2 successive scales, it is the same h, and I convolve and then downsample by a factor of 2. Downsampling would mean essentially throwing away every other sample. Similarly, you can derive a recursive relation for dm going by the same procedure, and here instead of g you would h you would have a g. This is once again convolution of g with A m minus 1, here also I have, but downsampled again by a factor of 2, that is it. So, I have the recursive relations that I want. I start off at a certain level. What level do I start off with? We will talk about it very soon, but I start off with a certain level at which I know the approximation coefficients and then obtain A and D recursively. It is a beautiful algorithm therefore, because convolutions can be implemented in a very efficient manner. So, equations 20 and 21 essentially summarize or give you the relations. In fact, there is a slight modification that I wanted to make. Let me make that in light of what you see in 20 and 21. It is not exactly convolution here, because a convolution would have been 2 k minus L, I am sorry about that. So, it should be convolution of A with H, reflected versions of H and G. So, there are 3 things that are different. Earlier we said 2, but there are 3 things that are different. One is that a regular convolution would have, if I denote this as k prime, a regular convolution would have h k prime minus L A minus 1 L. But I have L minus k prime, pretty much like what we have seen in continuous wavelet transforms and so on. So, I have this and likewise for this expression as well. Therefore, it is not a convolution with H, but a reflected version of H, and that is what you see in equations 20 and 21. Apologize for the mistake. Okay. So, we have two operations, of course, convolution and downsampling in addition to the reflection. Now, the question is what scale or what level do I begin at? The level at which I begin is the level at which the raw measurements are available. The raw measurements are available in form of a sample signal. I never have x of t with me. I only have a sample version of x of t. And what I assume therefore, if you look at now the schematic for the so called pyramidal or fast algorithm due to Mallet, this was in fact a breakthrough in the computation of DWT, pretty much like the way the FFT was a breakthrough in the computation of DFT. So, again coming back to the point, we assume that the signal that is available to me, the sample signal that is available to me is nothing but a set of approximation coefficients at scale at level 0. Now, is this true? Does this make sense? Well, first of all, remember that x of t, it is a continuous time signal, is sampled to obtain x of n. Now, for those of you who are familiar with sampling and linear algebra, sampling is nothing but a projection of x of t onto some basis functions, right. And we can treat x of n as some projection coefficients of x of t onto some basis space. We do not know what is that x of t, but we will say that I now have the approximation coefficients of some signal x of t which I do not know onto the wavelet basis space that I am, or the scaling function basis space that I am looking at. The recursive relations are between two successive scale levels, therefore, I do not have to worry whether I call the signal available signal at being at level 0 or level -1 and so on, but for convenience we will assume that it has level 0. So, the basic point is we assume the sample signal to be the approximation coefficients, and that is the best approximation you can have. If you want a finer approximation beyond what you have in sample form, you have to go back, sample faster and obtain the sampling sequence at a finer resolution in time. The resolution at which the sample signal is available is Ts. All the other approximations that I am going to construct, the coarser approximation coefficients that I am going to compute are going to be at poorer resolutions, but what do I gain? I gain on the frequency localizations. So, the time localization worsens as I go down the scale, go down the resolution or go up in M, but the frequency localization improves. So, let us now understand the algorithm. We have already looked at the basic equations. I start with the sample signal which is assumed to be A naught of n, convol with h, strictly speaking it is h bar and g bar, and then obtain this intermediate sequences. These intermediate sequences are at the same resolution, time resolution as A naught itself, because I have not performed any downsampling yet. The moment I downsample, then I obtain the desired coefficients A and D at a coarser scale, that is at a higher M. By our notation we call them as A1 and D1. Because of the downsampling, A1 has half the length as A naught and D1 has half the length as A naught. So, if you put together A1 and D1, that is you stack them up, the total length of A1 and D1 is going to be the same as A naught. So, we have not really increased the representation, the number of coefficients required that are involved are still the same. What we have done is some kind of a rearrangement. Think of A naught as being some bunch of colored balls. What we have done is we have rearranged the colors, and it is a nice example because the frequency bands correspond to some colors. What we have taken is done is we have taken a range of colors and taken balls in range of colors and put them in A1 with some modification, and then we have taken balls in another range of colors and done some modification and put it in D1. Now, the nice thing is ideally the frequency bands that A1 and D1 live in are non-overlapping. that means, and also the frequency bands corresponding to A1 and D1, the small a1 and D1 are different from the ones in A0. A0 has that is a sample signal has all frequencies from 0 to Nyquist frequency, that is omega max, whereas A1 has all frequencies in the range 0 to omega max over 2 under ideal conditions. It is more or less true, and D1 has the frequency range in the frequency range omega max over 2 to omega max. So, we have gained on the frequency localization, but we have lost out on the time localization because A1 and D1 are now spaced 2 Ts apart, and I repeat this exercise. Remember, I only need A1 to obtain A2 and D2, and as I move down here, as I come to A2, the frequency falls by a factor of 4. In fact, it is wrongly indicated that A1 A2 tilde here has 0 to omega max over 4, it should be ideally on A2, not on A2 tilde. And D2 would have frequency content in the range omega max over 4 to omega max over 2 and so on. So, when do I stop this decomposition? Well, that differs from application to application, and it is a user specified value. Theoretically, if the number of samples n is a power of 2, let us say 2 power big J, then you can go up to J, so that in the end you have one coefficient in your coarses decomposition, one coefficient in A1 and one coefficient in D1. So, that is the maximum level to which you can decompose. So, these are now we have what is known as a signal decomposition in the scaling function and the wavelet domain, but normally we call this as wavelet decomposition. These are not approximations or details, these are approximation and detail coefficients. They are different as we have seen earlier.